This is going to be a recap video of the Chapter 2 review live session. So you do need to read through this course information. It's going to have information about the test, so read through this on the PowerPoint, pause the video. But we're going to get started on this problem. This is actually from your classwork. I believe it was the last problem on your 2.3, 2.4 classwork. And I said on that classwork that it's a problem that the College Board really likes, so that's why I wanted to go over it. So I'm going to talk you through my thinking. You might have thought through it differently, but there are two different ways to approach it. I'll address both of them, but write the answer in one way. So this is we collected data on the tuition charged by colleges and universities in Michigan. Here are some numerical summaries of the data. The mean, standard deviation, minimum, and maximum. Based on the relationship between the mean, standard deviation, minimum, and maximum, is it reasonable to believe that the distribution of Michigan tuitions is approximately normal? So I want to start thinking under the premise that it is approximately normal. So what I'm going to do is I'm going to say if approximately normal, and then I'm going to draw a curve. So if this is approximately normal, I've got the mean in the middle, got my standard deviations. If this is approximately normal, I have now my minimum is going to fall about right here. This is going to be my minimum at 1,873. This would be my maximum over at 30,873. Okay, so I want to start thinking about, I can either attack this from the empirical rule or from the normal probability stance. So if this is a normal distribution, I can do normal calculations. So what I can do is I can find the probability that a value falls below right here. So what percent of value should fall below right there? That's what I want to figure out. So I'm going to define X as college tuition, or just tuition. Then I'm going to write a probability statement of the probability that X is less than 1873. And I'm going to do my normal calculation. So I'll have normal, labeling everything, CDF. My lower bound, because it's a left-tailed test, will be negative, or left-tailed problem, will be negative 1 times 10 to the 99. My upper bound will be that value, 1873. My standard deviation, or my mean, gotta go in order, will be 10,614, and my standard deviation will be 8,049. Then I will get that calculation, and that will give me about 0.1387. So what this is saying is, if this were a normal distribution, about 13.87% of data values would fall below 1,873. But in reality, no data values fall. So these are contradictory statements. So that's the statement that I would want to make, that I wanted to find a contradiction, so I wanted to disprove it. So I would say it is not reasonable to believe this distribution is approximately normal. That squiggly means approximately, because if it were normal, then about 13.87% of data values would fall below 1,000, I'm assuming it's dollars, $1,873. But that is actually our minimum value. So no data falls below there. This is a contradictory idea. So we could have also approached that from the high end on the maximum, but there's a much smaller percentage up there. We could have also addressed this using the idea of normal distributions in the empirical rule. So if I was looking at this for the empirical rule, I could go under the idea that this is 3 standard deviations, this is 3 standard deviations. and between negative 3 standard deviations and 3 standard deviations should be 99.7% of the data. But what we end up seeing is that the z-score for the minimum is actually going to be negative 1.09, and for the z-score for the maximum is 2.51. So we actually see that between negative 1.09 and 2.51 is 100% of the data. So if it were normal, 100% of the data would not fall between negative 1.09 and 2.51. So it's another way that you could tackle this. Either way is you have to just make a contradictory. You have to come up with a statement that could possibly be contradictory to prove that it's probably not normal. So what I wanted to also talk about was the connection between percentiles, z-scores, and quartiles. We started our unit with percentiles. A percentile is the percent of observations about less than or equal to. This is a change from the textbook, and I even amended this and skewed the script. I'm not sure if they adapted their video yet. But College Board would like us to describe the percentile as the percent of observations less than or equal to, not just less than. So we need to make that change accordingly. Well, how can we use this with normal distributions? We can find the percentile for a normal distribution by doing normal CDF. That's what we did here. We found this percentile. This was the 13th, closer to the 14th percentile. Okay? So that's how it's connected to normal distributions. We can find a percentile for any distribution. It's just going to be part out of whole. How our z-score is connected to all of this. A z-score is a standardized score. So we could standardize the score. Then we could do normal calculations with a standard normal distribution. A standard normal distribution is normal with our mean of 0 and a standard deviation of 1. Okay, so that's another way we could do it. Quartiles are just a fancy name for percentiles. So 25th percentile is the first quartile, 75th percentile is the third quartile. So they all play into normal curves. But here's a big idea that some of you are probably going to struggle with. That I can standardize values for any distribution. The distribution could be skewed to the left, it could be skewed to the right, it could be approximately normal, it could be uniform, because symmetric and uniform are not the same thing. But I can only use normal probability calculations for normal distributions. Let me repeat that. I can only use normal probability calculations for normal distributions. So if in part A, let's say this was part A, in part A, you were asked to decide whether this was a normal distribution or not, and you said it's not reasonable to use a normal distribution. In part B, if you were asked to find the z-score, I could find the z-score, but I cannot do normal calculations. I can only do normal calculations in problems where I'm told it's a normal distribution. Okay, so standardizing we can do for anything that's to make comparisons. It's kind of like when we did graphs in chapter 1 where we turned everything into percentages so we can compare parts to wholes. It's the same idea here. I got this question and I want to address it because I feel that I did not do a good enough job of addressing this question, so I want to make sure that I addressed it. It says, why is the probability of x is less than 5 the same as the probability that x is less than or equal to 5? The same thing for a normal distribution. Now remember, when we do normal calculations, we only use normal CDF, not normal PDF. So, in a distribution, let's say this is 5. I don't actually know what that, I'm just making this up. Let's say this is 5. If I wanted to do less than, I would just shade with the, I'm going to shade like this. This would be all the values less than. Now, what I'm going to do to get that probability is I'm going to take every single probability underneath here, every single one. That's a bunch of probabilities. So what's going to happen is that's going to take me forever. I'm going to add up so many individual little data points and I'm going to get my final answer. The difference between the probability that x is greater than or less than or equal to 5 is going to be adding just this single line. Just that line. That area for that single line, think about the line of a pencil if you were to draw it. The area of that line on a piece of paper or anywhere is so negligible it's not going to make a difference. So really, if you do these problems, you could write less than 5 or less than or equal to 5. The same idea goes for the probability that x is greater than 5 versus the probability that x is greater than or equal to 5. These are all going to be roughly the same thing. And again, it's because the area under that curve is so small, it's negligible. It doesn't really matter. So keep that in mind. If you're looking at an at least problem, you really could write it either way. Technically, at least is talking about this one. At least is greater than, including that one, or greater than. So something to think about. Always, these are reminders from your notes. I did forget you always need to define variables. So you need to label a curve. Do that, people. Make sure you draw your curve and label it. Here's my curve. Labeling is like this. Then I need to define my distribution. That's going to be writing n. Define my parameters. That's going to be mu comma sigma. Put the numbers in there though. Show your work. That's going to be normal CDF, never normal PDF, or inverse norm. And then you need to finish it off with a sentence. Make sure you label in here. Label. If you don't label, no credit. No labels equals no credit. That's not my decision, that's AP's decision. So take it up with them if you have a problem. Here's a problem from a multiple choice question. I know there's no answers because I took them away because I thought we could just do it free response. So we are going to look at this one as a free response question. And we'll find the answer. So it says the weights of the population of adult male gray whales are approximately normally distributed with a mean of 18,000 and a standard deviation of 4,000. So what I'm going to do is I'm already going to write one thing that I have. That's n, the normal distribution for the grays. It's going to be 18,000, comma 4,000. Mean, standard deviation. The weights of the population of adult male humpback whales is approximately normally distributed with a mean weight of 30,000 and a standard deviation of 6,000. So I'm also going to note that. Humpback whales is going to be 30,000, comma 6,000. Now I'm going to see what else I need. A certain adult male gray whale weighs 24,000 kilograms. So I have X gray whale, that's just his value, is going to be 24,000. The whale would have the same standardized score, this is the important part, it would have the same standardized score as an adult male humpback whale whose weight is in kilograms. And that's what we're finding. So we are finding X of the humpback whale. But we were given an important piece of information here. We were told the standardized score, that's our z-score, for the gray whale is equal to the standardized score of the humpback whale. So if we rewrite that using the formulas, that's going to be X of the gray whale minus mu of the gray whale over H of the sigma of the gray whale is going to equal X of the humpback minus mu of the humpback over sigma of the humpback. And we actually have almost all of these values. We have all of these, this one, and these two, so the only one we need to find is that guy right there, and that's what we'll do. I'm going to do it separately because I don't like to write it all together. I like my things to be separate. That's just a personal preference. So I have my z-score for the gray whale is going to be 24,000 minus 18,000 divided by 4,000, which will equal 1.5. That's my z-score, which I also know is going to be the z-score for the humpback whale. So I'm going to take that, and I'm going to have the z-score for the humpback whale that's going to be 1.5. So I'm going to do the stuff for the humpback whale. 1.5 equals, I'm looking for the value of the humpback whale, minus the mean, which is 30,000, divided by 6. So when I multiply both sides by 6,000, I'll get 9,000 equals the value of the humpback whale minus 30,000. So I'll get the weight of the humpback whale to be 39,000 kilograms. And that would have been the correct answer when we solved it. I just think this problem's really good because it makes you really think about what you need, what you have, what you need, and how you're going to solve it. So normally we would do a Frappy together, but we just don't have time for that this chapter, so I'm going to do this for you, and then there is grading, so you can pause the video, or you can look at the PowerPoint to look at how it would have been graded to verify that whether you would have gotten all the points. You could also pause it right now, try the problem, and then play it again to see how you did. So this is a Frappy. It says the distribution of scores on a recent test closely follows a normal distribution with a mean of 22 points and a standard deviation of 4 points. So I'm going to note that right away. Normal distribution, 22, 4, and I'm going to define my variable as x equals test score. So I don't have to think about that again. So it says, what proportion of students scored at least 25 points on this test? So I'm going to first draw my curve like I should be on every problem. So I have 22 in the middle. 25 is bigger, so I'm going to do my standard deviations to the right. So 26 and 30. Then I'm going to shade where my value is. So 25 is right here. I'm labeling that. And I'm also going to shade. So I want at least, so I want above that. So I'm going to find, I already defined x, the probability that x is greater than or equal to or greater than, here it doesn't matter, 25. And because I have, so this is a note I want to make to myself. I have a value. I need a percent or a proportion. So I'm finding, or I'm using normal CDF. We don't want to mix up normal CDF and anything else. Inversion norm. So I have normal, I'm labeling normal CDF. Lower bound, this is bounded on the left, that's the left boundary, is going to be 25. Upper bound, that's going to be my right boundary. There is no right boundary, so I'm going to have 1 times 10 to the 99. We want to go as large as possible. My mean will be 22, and my standard deviation will be 4. Plug that into my calculator, and I'm going to get 0.2266. So I could write this answer, because I need to write a sentence now, 2 different ways. I could write this answer, and I could say that about 22.66% of students scored at least 25 points on the test, or I could go the route with the proportion, and I could say the proportion of students who scored above a 25, or at least I guess would be the correct wording. I want to match the problem. 25 points on the test is about 0.2266. So I always use about, approximately, roughly, because I had to round. So even if you're not rounding, it's always a good idea to just make sure that you are using about, approximately, etc. So that is if I need to find the area under the curve. Now I have what is the percentile, what is the 31st percentile. I'm rewriting this because I'm neurotic and like to make sure that it's covered. So 31st percentile, I'm doing the other type of problem here. Now I have the percentile, which is going to be the proportion or the percent. I guess it's going to be all of them included. I need the value, so I'm going to use inverse norm. Always need to draw my curve. This one's a little harder to estimate where the percentile is. So the middle's 22. Now I know that from this way is going to be 50% of the data. So I don't want to the 50%. So I'm going to put another standard deviation. That's going to be 18. And I know that between these two, because I'm thinking about the empirical rule, that's 34% of the data. So that means 16% falls this way. And I need 31%. So 31% is going to fall somewhere in between the first standard deviation and the mean. So I'm just going to say it's right here. I just need a general idea. And then I'm going to shade. This percentile is up to and including, so that's how I know to shade that direction. So I'm going to be looking for the probability that x is less than some number or less than or equal to some number, which equals 0.13. And I'm finding this. So I need to use inverse norm. So I have inverse norm equals, do not put these two equal to each other, they're not. Or sorry, you don't want equals there. You want the area, labeling again, 0.13, comma the mean, 22, the standard deviation, 4. That's going to give me a value of 20.02. So then I just need to put it in a sentence. The 31st percentile for the distribution of test scores is about 20.02 points. Again, I used about. Included everything I needed, and this is an A+ problem. Now, you can pause this and look at the scoring for part A if you want to make sure we got everything correct, or if you got everything correct after you've already done it. And you can do the same thing for part B. You can pause it and look at it. We're going to do part C. There was a part D, but I got rid of it. So it says the teacher wants to transform the test scores so that they have an approximately normal distribution with a mean of 80 and a standard deviation of 10. So I'm writing out my new test score. So I'm going to do n sub n because new. Defining my variables is going to be 8, 10. I'm actually going to note my old ones. So I'm going to say O is going to be old score. So my distribution was n sub O. That was 22,4. Now we need to recall, because this didn't go away, what is affected by adding and subtracting and multiplication and division. So adding and subtracting affects center and location. So percentiles and exact values. Does not affect spread or shape. Multiplication and division affects center, location, and spread, but shape is never affected. That's why if we went from a normal distribution, we can go to a new normal distribution, because one of them was normal, the new transformed distribution will also be normal. So she wants to figure out what this A and the B, find the values of A and B, so the teacher can transform this data. She knows where she started and where she wants to end. She's going from here to here. We need to figure out what A and B are. So essentially, we should be thinking back to Algebra 2, how we need 2 equations to solve for 2 unknown variables. But we also want to fill in what we have. So this is very similar to the taxi problem in the 2.1 and 2.2 classwork. It should have been the last one. So I'm going to have the mean of the new score is going to equal, and mean is affected by adding or subtracting. So plus A plus B times the mean of the old score. Now for the standard deviation of the old score, that's not going to have A, because A is adding or subtracting does not affect standard deviation or measures of spread. So it's going to be B times the standard deviation of the old score. And this should be N, sorry. So now I'm going to plug in what I have, and I see this equation has 2 unknown variables. The second one does not. So I want to work with the second equation. So I'm going to plug in what I have, and that will be the new standard deviation needs to be 10. I need to find B, and my old one is 4. So I'm going to divide 4 by both sides, and I'm going to get B equals 2.5. That is B. Then I need to plug that in to here and solve for A. So I'm going to do some more math. I know my new mean that I want is 80 equals A is what we're looking for. B we have, it's 2.5, and my old mean is going to be 22. So I'm going to solve this. 2-step equation, actually 1 step, because you're going to multiply 2.2 times 22, and I'm going to get 25. So then, to get full credit, I'm going to write my new transformation. So the new score should equal 25 plus 2.5 times the old score. You can look at the grading to see how to grade it, to make sure you would get all your points. There was part D, like I said, I got rid of it because we actually kind of already did that. No time for other questions, unfortunately. You do have a student survey due the 30th, and I highly, highly suggest watching the video that I posted over 2.3 and 2.4 extra examples. I'm not really sure how you did the classwork without watching that video, but that would be my suggestion, would be to watch that video.